All right. I apologize. My cat is making biscuits on top of me. But let's do this 2023 FRQ for AP Chemistry. Number one, manganese has several common oxidation states. No one cares. Write the complete electron configuration for a manganese atom in the ground state. Ground state just means not excited. Electron configuration is this stuff: 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d5. Sorry, whoops. I skipped the 4s2. 4s2, 3d5. So manganese is the fifth atom in the transition metals, so it's got the 3d5, but it's still that 4s2 row because it's the fourth period. When manganese forms cations, electrons are lost from which subshell? So electrons are lost from the valence shell first. So the valence shell is the one with the largest number. So this, in this instance, it would be the 4s shell. If it had a 4p shell, it would be the 4p shell, but it doesn't have a 4p shell. Student performs an experiment to produce a manganese salt of unknown composition, manganese chloride, to determine its empirical formula. Cool. Let's see. B. Calculate the mass of chlorine in the sample of manganese chloride in the beaker. So this is the mass of the beaker with manganese, and this is the mass of just manganese chloride. So if we subtracted manganese chloride from manganese, we would have the mass of the sample of just the mass of chlorine. God, sorry, my cat's tail is on top of the drawing pad. There we go. 62.673 minus 61.262. And that gives us 1.411 grams of chlorine. Calculate the number of moles in the sample. So we just have to go from grams to moles. So 1.411 grams chlorine times the reciprocal of the molar mass of chlorine, which is 35.45 grams per mole. Oh, now she's kneading on my arm. It really hurts, actually. That answer is 0.03. Yeah. That's 0.03980 mole of chlorine. She is a good cat, but she is really getting in my way right now. Lily, yes, you are so good. The student determines that 0.0199 mole of manganese was used in the experiment. Use the data to determine the empirical formula of manganese chloride. So when you have moles of the substances, so we have 0.0199 mole of the manganese, we have 0.03980 mole of the chlorine. You just divide by the lowest number of moles. But if you're finding the empirical formula, make sure you're in moles before you divide by the lowest number. So we're going to divide by 0.0199. We'll divide by 0.0199. This just gives us the molar ratio. So 0.0199 divided by 0.0199 is 1. 0.3980 divided by 0.0199 is 2. So our formula is manganese 1, don't have to write the 1, chloride 2. Okay, let's see. E, the student repeats the experiment using the same amounts of manganese and HCl, but some of the manganese chloride splashes out of the beaker. Will the number of moles of chlorine calculated for this trial be greater than, less than, or equal to? So it'd be less than, right? If we lost some manganese chloride, that would reduce this number, which would reduce this number of grams, which reduces the number of moles. So you'd say less than for that explanation. Okay, let's move forward. F. Based on the half reactions given in the table, write the balanced net ionic equation for the reaction that has the greatest thermodynamic favorability. I'm actually going to skip to number 2 first. So write the value for E naught cell for the reaction. So the equation is cathode minus anode. Normally, we want to just maximize and make it the most positive that it could possibly be. So if we take this one and subtract it from this one, that would be the most positive value that you could get. So 0.15 minus negative 1.28 gives us 1.43. So again, you want to maximize and make E naught as positive as possible. So now we know for our balanced net ionic equation, we know this one's forward and this one is reversed because we said this one was the anode. So let's write out that bottom equation, 2MnO2 solid plus H2O liquid plus 2 electrons. And now my cat is being so good. She's just staring at me. She is the best cat in the world. Manganese O3 solid, 2OH minus, classic. And then this middle one, we're going to write out reversed. because we flipped it to maximize thermodynamic favorability. Aqueous zinc oxide solid plus H2O liquid plus 2 electrons. So this is like the overall two equations, but it asks for the balanced net ionic. So when you do the balanced net ionic, you just cross out what's on either side. So the 2 H2Os are on either side, 2 electrons are on either side, the 2 OH minuses are on the other side. Then you just add it up. So we have 2MnO2 plus zinc makes zinc oxide plus Mn2O3. And that's the answer. So it's just the products, the reactants and the products. Calculate the value of delta G in kilojoules per mole reaction. So for this equation, we have moles of electrons, we have E naught, so we're gonna use negative N, which is moles of electrons, NF E naught. F is Faraday's constant. N is moles of electrons transferred. 2 moles of electrons are transferred. So N is 2. Faraday's constant is 96,485. And our E naught was calculated in part 2. It was 1.43. This will give us an answer in joules. We want it to be in kilojoules, so we're just going to divide by 1,000. That gives us negative 276 kilojoules per mole reaction. Part 4, the student claims that the total mass of an alkaline battery decreases as the battery operates because the anode loses mass. Do you agree with the student's claim? So first of all, this net ionic equation doesn't demonstrate any loss of mass. So that's untrue inherently. But also, this battery's enclosed. No gases are escaping. No mass can change. So it's a disagree for either of those two reasons. The battery is enclosed, or the equation demonstrates no change in mass. The anode gains the mass from the cathode. Number 2. Nice. Finished number 1 real quick there. Only 7 minutes, 30 seconds. Oh, there was one thing I wanted to mention. Whoops. In part AI, you could have written the shorthand notation. So instead of all of this nonsense, you could just write the noble gas, which is represented by this first part, this part here, and then you could just write the 4s2 3d5. So if you're wicked smart and you like to just use the shortcuts, go ahead, you can. That is an acceptable answer. All right, part 2, number A, letter A. Part 2, number A, classic. All right, how many grams of chlorine can be formed from 1.25 moles of AlCl3? So just a stoichiometry question. Let's start it out with our moles of AlCl3. For every 1 AlCl3, we produce 3 chlorines, so let's write out that. Oops, 3 moles chlorine for every 1 mole AlCl3. And then, now that we're in moles of chlorine, we want to find grams of chlorine, so we just multiply by the molar mass of chlorine. That gives us our answer. So this is a 3, by the way. No, that's not most neat. That gives us an answer of 133 grams of chlorine. All right, part B, calculate the value of delta H1 in kilojoules per mole reaction. So this is a Hess's law question. The premise is we're going to add up all of these 3 to form this top equation. So let's start with the very first thing we need. We need AlCl3 as a reactant, and we just need one of them. So we need it as a reactant. This has it as a product, so we have to flip this equation. So we'll say times -1 for this delta H, and I'll write it out just to demonstrate how you could do this. So since we're flipping it, it would be the AlCl3 gas on the left, and then the solid aluminum and the 1/2 chlorine, 1.5 chlorine gas on the right. So that gives us our AlCl3 as a reactant. Boom. Do a little check mark there. We need aluminum gas. So we just produced aluminum solid, so let's now make it into a gas. Looks like we just got to do that one time. So just write that out. And now we could cross out these aluminums because they're on either side. So this, we don't need to change this value because we didn't change this at all. We had to multiply this one by -1 because we flipped that equation. Then this very last one, we're looking for 3 chlorine gases, so we're good on the aluminum gas. We're looking for 3 chlorine gases and not Cl2, just Cl all on its own. So it looks like we have to do this 1.5 times or 3/2 times. So we'll multiply this bottom one by 3/2 times 3/2 times 3/2 because 2 times 3/2 is 3, and that would give us the 3 chlorines. So that bottom one, 3/2 Cl2 gas. Oh, I gotta scroll down. I'm running out of space here. To make 3 chlorine gas. And we can cross out this, and you can see that we have AlCl3 plus, or creates aluminum gas plus 3Cl gas, and that's what we were trying to make for reaction 1. Now we just add up all of these. So this times -1, this just plain and simple, this times 3/2. So we just add up all of these and we get a answer of 1274 kilojoules per reaction. Just to write out the math for that, it would be -583 times -1 plus 326 plus 243 times 3/2. And that gives us our answer here. Okay. C. Based on the graph, what is the bond length in picometers for Cl2? So this is a potential energy diagram for Cl2. As we go further left, you get repulsion. As things are too close, as you go further right, you get attraction. And then right here where the graph peaks, this is the ideal bond distance. So where it dips down rather than peaks. So you can see it looks like this is about 200 picometers is right where that dip is. So the answer is just 200 picometers. All right, part 2, a student finds that the average aluminum Cl bond length is 220 picometers and the average bond energy is 425 kilojoules per mole. So it's got a length of 220, so our dip should rest at this 220 mark, and then it's a bond energy of 425. So the dip should be right here, and let me just connect it from there. The important part really is that the dip is right here. Okay. D. 3 proposed Lewis diagrams for the AlCl3 molecule are shown. Has a trigonal planar geometry. Which diagram can be eliminated based on geometry? So this one would be trigonal planar because there's no lone pairs on the aluminum. This one would also be trigonal planar because there's no lone pairs on the aluminum. But this one, since there's lone pairs on the aluminum, this shape, this molecular geometry would actually be trigonal pyramidal. So diagram 2 can be eliminated because there are lone pairs, which makes it trigonal pyramidal. Okay, which of the 3 diagrams is the best representation for the bonding in AlCl3? Justify your answer based on formal charges. So let's write out the equation for formal charge. It is formal charge equals valence electrons minus, in parentheses, number of bonds plus number of electrons in lone pairs. So it's like so number of electrons in lone pairs, like right here, this would be 2 number of electrons in lone pairs. Let's do an example here. So chlorine has 7 valence electrons. So 7 minus number of bonds, 1. 7 minus 1 is 6. Minus number of electrons in lone pairs. There's 1, 2, 3, 4, 5, 6 electrons as lone pairs. So this chlorine has a formal charge of 0. How about this aluminum? Aluminum has 3 valence electrons, and there's 4 bonds here. 1, 2, 3, 4. So this aluminum has -1. These 2 chlorines are the same, so formal charge of 0. This chlorine, so again, 7 valence electrons minus the 2 bonds makes 5, minus the 4 electrons as lone pairs makes positive 1. So this is immediately not a good diagram because if you have to have a formal charge, your diagram must have a charge. You would prefer that the negative charge be on the more electronegative atom. So chlorine's more electronegative than aluminum, so it would be better if these were flip-flopped, and that's not the case here. Diagram 2 we already eliminated in part 1. That really only leaves us with diagram 1. We saw that this was 0, this was 0, this was 0. Let's see. Aluminum has 3 valence electrons minus 3 bonds makes this 0. So diagram 1 is the best because it has formal charges of 0. All right, write the expression for the equilibrium constant Kp for this reaction. So this is our reaction. We want to write the Kp. K is always products over reactants. The only thing that you need to make note of is when it's Kp, you need to write P. Still goes in the brackets though. This is not squared because its coefficient is 1. This one would be squared though because it has a coefficient of 2 in the balanced chemical equation. So Kp squared. 2 becomes the squared. Particle level diagram of an equilibrium mixture of this. Okay, cool. Using the particle level diagram, calculate the value of Kp for the reaction if the total pressure in the container is 22.1. So let's deduce some things here. P total equals P1 plus P2. This is on your equation sheet. I think, actually, I'm not sure. Let me see. Yeah, it is. It's under gases, liquids, and solutions on the second page of the equation sheet. It actually says P total equals PA plus PB plus PC plus ... But we could just say P total equals P1 plus P2 for the purpose of this problem. So let's now figure out what the pressure of each one is individually. We have 1, 2, 3, 4, 5, 6, 7 AlCl3s. We have 3 Al2Cl3s, Al2Cl6s rather. So we could say 3/10 of it is Al2Cl2 and 7/10 of it is AlCl3. So let's say, let's plug that into our Kp expression. Let me scroll down here a little bit. Ah, Lily! Ah! Oh, she's so good. All right, so 3/10 times 22.6 is our, or 22.1 rather, is this top part over 7/10 times 22.1. But in our Kp expression, that was squared. So we would square this part, and that equals 0.0277. Number 3, on to number 3 already. All right, write the balanced net ionic equation for this reaction. So when we're writing balanced net ionic equations, solids don't separate, but aqueous components do. Gases, liquids also don't separate. So we could say this is H plus. Oh God, she's licking me, and it tickles. Plus Cl minus, and this is Ca2 plus. Ah, stop licking me. Plus Cl minus. So since 2 Cl minus occur on either side, right? This is Cl2, this is 2 Cl. We could cross out the Cl minus, so we'd be left over with CaCO3 solid plus 2H plus creates Ca2 plus CO2 gas plus H2O liquid. Sick. The student correctly identifies that trial 5 is inconsistent with the other trials. Explain why the student's claim is correct using the data. So let's see, trial 5 is inconsistent. It's small chunks and the time it took was 227 seconds, which is unusual because large chunks took less time than the small chunks. So that makes no sense. So it's inconsistent because the smaller chunks took a longer time than the large chunks, which doesn't make sense because trial 5 should have a larger surface area than trial 6. So that's the explanation. Surface area and rate are proportional. All right, part C. Based on the reaction conditions and the collisions that occur between particles, explain the reason for the difference in the reaction times between trial 2 and 3. So between trial 2 and 3, we go from small chunks to large chunks, and you can see the time of reaction increases, so the rate decreases. So because there's a smaller surface area in the large chunks compared to the small chunks, you have less room for collisions to occur, so the rate of the reaction decreases. So lower surface area decreases rate of reaction. We could say lower surface area decreases rate. And you should probably explain that more. A lower surface area has less space for collisions and all that jazz. It's kind of hard for me to write with this pen. The student claims that the reaction is zero order with respect to HCl. Do you agree or disagree with the student's claim? Let's take a look at our chart. So here, concentration of HCl is 1 molar. Time of reaction 67 seconds. Here, our concentration is 3 molar, 22 seconds. I chose 2 trials where they were both fine powder. That way we could compare just fine powder. So we can see as we increase concentration of HCl, the rate increases. So if it was zero order, that would not be the case. The concentration of HCl would affect the rate. So we're going to disagree since the concentration of HCl affects the rate. The HCl was present in excess in all trials of the experiment. Determine the molarity of the HCl in the beaker after reaction is complete in trial 2. Assume that the volume of the mixture remains constant at 50 milliliters throughout the trial. So we're going to want to find the initial moles of HCl that we have, and then the final moles of HCl, and then divide by 0.05 liters, which is this converted to liters. So let's first figure out how much reactant reacted. So, and which trial is this for? For trial 2. Okay, so we're looking at this trial here, which is 1 molar. So it's 50 milliliters of the HCl, and it's 1 gram of the calcium carbonate. For every 1 calcium carbonate, there's 2 HCl's. So I think that gives us all the information we need. All right, let's start it. 1 gram CaCO3 times the reciprocal of the molar mass, which is given to us, 1 mole. I'm just going to use 100 grams CaCO3. Always indicate what moles you're talking about. And then the molar ratio was 2 HCl for every 1 CaCO3. So this gives us how much HCl reacted, the moles of HCl that reacted. Okay, so 1 divided by 100.001 times 2, or sorry, 0.01, and then times 2.02 moles of HCl. So this is how much reacted. Let's figure out how much we had to start. We had 50 milliliters. Let's convert that to liters. 1 liter for every 1,000 milliliters. And then times, it was 1 molar, because this is trial 2. Trial 2 is 1 molar. So times 1 mole per liter. This is 1 mole of HCl. Liters cancels, milliliters cancels. We're left with moles HCl. This gives us our initial amount of moles. 50 divided by 1,000 is 0.05 times 1 is still 0.05. So this is how much we had initially. Let's say initial. So we would take the initial minus the amount that reacted, so 0.05 minus 0.02. That equals 0.03 moles HCl, so that's how much is left over. So I'll say left. Okay, but we wanted molarity, determine the molarity. So this is moles, we need molarity. So we're going to divide by the volume, which is 0.05 liters. So 0.03 moles divided by 0.05 liters. That gives us 0.6 molar HCl. All right. Part F is the reaction endo or exothermic. All right, so we can see Temperature's increasing, 21.2 to 21.9, so it's exothermic. And you would just say temperature is increasing. All right, part G. So since the temperature of the solution is increasing, the reaction is releasing energy into its surroundings. That's your justification. Since the temperature is increasing, since the temperature of the solution is increasing, the reaction is releasing energy into its surroundings. G, part I, calculate the magnitude of heat transfer Q in joules. So we're given mass, specific heat, so we're definitely going to use Q equals mc delta T. So we're looking for Q. M is given to us as 51 grams. That's the mass of the whole system it specifies. Times, let's see, C is given to us as 4. We don't need to convert anything to Kelvin because we're in Celsius here and we're in grams, so we're good. So times 4. And then our change in temperature between here and here, this is a change in temperature of 0.7. I could write that out. 21.9 minus 21.2. So our final minus our initial equals 0.7. So times 0.7. And that gives us 140 joules. Okay. That's a 1. Part 2, calculate the enthalpy of reaction in units of kilojoules. So let's just go ahead and convert this to kilojoules right away. So times 1 kilojoule for every 1,000 joules gives us 0.14 kilojoules. And the next part of enthalpy is that it's per mole reaction. So we will need to find out how many moles reacted and therefore how many reactions occurred, and then divide that by this. Another thing that's important to note is this is enthalpy. We already determined that this was an exothermic reaction, so our final answer should be negative. The proof for this is the Q of the reaction is equal to negative Q of the surroundings. So all energy lost to, this is a Q, not a 9. All energy lost by the surroundings is produced by the reaction. So since we got a 140 joules for Q of the surroundings for the system, the Q of the reaction must be negative 140 joules. So we could say this is negative 0.14 kilojoules. But we also know this because it's exothermic, our delta H must be negative. But anyways, okay, we found kilojoules. Let's find moles of reactions. So it's 1 gram of calcium carbonate. Takes 1 mole of calcium carbonate for every 1 reaction. So let's figure out how many reactions occurred. 1 gram calcium carbonate was our limiting reagent. We already determined the molar mass of calcium carbonate was 100 grams. That was given to us in a prior problem. And then it is 1 calcium carbonate for every 1 reaction. Let's go prove that real quick. 1 calcium carbonate produces 1 reaction. A whole reaction takes 1 of these. Okay. So that means we had 0.001 reactions. Or, sorry, I keep messing that up. 0.01 reactions. So let's divide kilojoules by reactions. That gives us 14 kilojoules per reaction. Per mole reaction really is the notation. But again, it's supposed to be negative because it was exothermic. So per mole reaction. Cool. Cool, cool, cool. Part 4, number 4. For the calculate the mass of CH3NH3Cl that contains 0.0025 moles. Okay, so this is just stoichiometry. We're just going from moles to grams. We need the molar mass of CH3NH3Cl, so let's determine that real quick. Molar mass, carbon's molar mass is 12. Molar mass of hydrogen is 1, and there's 6 hydrogens, so 12 plus 6. Molar mass of nitrogen is 14. Molar mass of chlorine is 35.45. So the overall molar mass is 67. it's 67.45 if you do it this way. If you do not round these numbers, which you should not round them, I'm just rounding them for laziness, the molar mass ends up being 67.52 grams per mole. And now we can just go from moles to grams. So 0.0025 moles times 67.52 grams per mole. Moles cancels. We find that it is 0.169 grams of CH3 NH3Cl. This next problem is pretty fun. Part B, the following table contains a partial procedure for making a buffer solution. Fill in steps 1 and 4. All right, so in step 2 says place the solid in the 50 milliliter beaker. So that means in step 1, we must have weighed out the solid. This is our solid, so we would say this goes here. To weigh out a solid, we're going to need a balance. We're going to need to use weighing paper, and we're probably going to want a spatula to pour the solid. So you would say weigh out 0.169 grams of this using electronic balance, weighing paper, and small spatula. All right, step 3, clean the burette and rinse with distilled water. Part 4 is blank. Part 5, use the burette to add 25 milliliters of 0.1 molar CH3NH2. So if we're adding this to the beaker using the burette must have been filled with this. You also must prime with it. So we're going to say prime with this, and then fill with it as well. So prime and fill with that CH3NH2. All right. Part C, the student prepares the second buffer solution. The student uses 25 milliliters of this instead of this. Oh, and half the mass of this that was used in the first buffer. So they used half the molarity of the base and half the mass of the conjugate acid. So the buffer is still going to have the same pH because the moles of acid and base were both decreased by half. So the ratio of moles to base is still the same. So equal to, and you could just say ratio is 1 to 1 still of moles to base, or of acid to base. Okay, number 5. Let's go. Calculate the number of moles of HCl in the container. A sample of HCl is stored in a rigid 6-liter container at 7.45 atm and 296 Kelvin. Let's use Puvnert. If we want, we could solve for moles. N equals PV over RT. P is given to us as 7.45. Liters is given to us as 6. R is 0.08206. We're using 0.08206 because we're in ATMs. If we were in torrs, we would use the other value. If it was torr, we would use 62.36 for R. But we are given ATMs. All right, and then our temperature is 296 Kelvin. So this works out to be 1.84 moles. Part 2, the rigid 6-liter is cooled to this temperature. Calculate the new pressure. There's 2 ways you could do this. We could do the classic P1 over T1 equals P2 over T2. So P1 is our initial pressure, 7.45. Our initial temperature is 296. And our new temperature is 271. So it would be over 271, and we'd be solving for P2. The other way you could do it is you could also just use Puvnert using this known amount of moles. This is a rigid container. It doesn't indicate any loss of moles. So we could just say pressure times 6 liters equals 1.84 moles times 0.08206 for R times, and it says in ATM, so we're going to continue to use 0.08206, and then our temperature is 271. So either way, you can solve it like this or like this. Either way, you're going to get an answer of 6.82 ATMs. So pick one, whatever works for you. You could use the Gauss law, or you could use, I forget which one this is. This might be Gay-Lussac's or Charles or Boyle's. I don't know. All right, when HCl ionizes in an aqueous solution, ions are formed. Chloride ions are formed. Draw 3 water molecules with proper orientation around the chloride ion. Use this as little Mickey Mouse to represent water molecules. So in our Mickey Mouse diagram, these are the darks are the H's. The O is the oxygen. Oxygen is more electronegative, so this side is a little negative, and these are a little positive. So the hydrogen should be facing the chlorine, and the oxygen should be facing away. These are coming out terrible. It says to draw 3. There we go. So hydrogen's facing the chlorine because the hydrogens are partially positive, the oxygens are partially negative. You don't have to label that part, you just have to draw it, right? It just says draw 3 water with proper orientation. Okay, part C. Ka values for the 3 acids are shown in the preceding table. The following particulate diagram represents the ionization of one of the acids in the data table. Water molecules have been omitted for clarity. Which acid is represented in the diagram? So Ka is a measure of acid strength. The formula for Ka is H plus squared over Ha. Or you could say it's H plus times A minus over HA. And these should be in brackets as well. This is a multiplication symbol. Either one works just fine. So it looks like we have 1 A minus and 1 H plus. H3O plus is the same as H plus. So we could say our top value is a 1. And our HA, 1, 2, 3, 4, 5, 6, 7, is 7. So this is clearly some sort of decimal. I don't know what the decimal is. But let's look at these Ka values. This one is a decimal, right? It's times 10 to the negative 4th. This one is a huge number, right? This is like 2,000,000,000. And then this is even bigger. So it's got to be HNO2 because it's a decimal. It's got the closest Ka. So you justify by just saying it's got the closest Ka. It's the only one with the Ka less than 1. All right. List the types of IMFs present in pure samples of HBr and HF. Classic intermolecular forces question. Hydrogen bonding takes what? What does hydrogen bonding take? It takes a nitrogen, oxygen, or fluorine, and a hydrogen has to be bonded to one of those 3. So HBr does not do hydrogen bonding, but HF does. So say hydrogen bonding. If something has hydrogen bonding, it does also have dipole-dipole because hydrogen bonding is really just a strong form of dipole-dipole. And then, of course, it also has London dispersion forces. Everything is London dispersion forces. HBr also has London dispersion forces. Doesn't have hydrogen bonding because there's not a nitrogen, oxygen, or fluorine bonded to that hydrogen. But this is a polar molecule, so it is dipole-dipole. B part I, based on the types and relative strengths of intermolecular forces, explain why delta H vape of HF is greater than that of HBr. So heat of vaporization, delta H vape, is the energy it takes to boil something. So it takes more energy to boil HF than it does to boil HBr. This is because the hydrogen bonding is so strong, it makes it harder to boil HF. It's harder to pull apart the HF molecules because it's got those strong intermolecular forces with the hydrogen bonding. So you would really just say H bonding makes it harder to pull apart the hydrogen fluoride, which increases the delta H vaporization of hydrogen fluoride. Calculate the amount of thermal energy in kilojoules required to vaporize 6.85 grams of HF. So let's just go ahead and find the moles of HF. Kind of just a good principle. The molar mass of fluorine is 19. Molar mass of hydrogen is 1. So this is 1 mole. So that's 20 grams, right? 19 plus 1 is 20. So we have 0.3425 moles of HF. And the heat of vaporization is this. whoops, that is my bad, is 25.2 kilojoules per mole. So we just multiply this by 25.2 kilojoules per mole. And we are left with our answer, which is 8.63 kilojoules. Part C, based on the arrangement of electrons in the B, R and F atoms, explain why the bond length in an HBr molecule is greater than that in an HF molecule. So fluorine only goes to, let's see. So fluorine has an electron configuration of 1s2, 2s2, 2p6, 2p5 rather. Br has an electron configuration of 1s2, 2s2, 2p6, 3s2, God, 3p6, 4s2, 3d10, 4p5. So, bromine has more electrons, which increases its radius. Since it has a larger radius, its bond with the hydrogen must be bigger because it's more spread apart. So that's your explanation. Okay, number 7, final question. The student draws a particular diagram shown to represent the ions present in an aqueous solution of SrOH2. So 1 Sr for every 2 OHs. What is the error in the student's drawing? So let's see, 1, 2, 3, 4 SRs, 1, 2, 3, 4 OHs. But the ratio should be 1 to 2, so incorrect ratio. And I'll reiterate that. Sorry, I am speeding through this. There's 4 Sr2 pluses, and there's 4 OH minuses. But for every 1 Sr, there should be 2 OH minuses. So if there's 4 Sr pluses, there should be 8 OH minuses. All right, part BI. Calculate the value of OH minus in the solution. The student determines that Sr2 plus is 0.043. Oh, okay. So for every 1 Sr2 plus, there's 2 OH minus. So we could just say 0.043 times 2 equals 0.086 molar OH minus, which equals OH minus. We know that it's in a 1 to 2 ratio because it's saturated and it doesn't indicate any other ions, any other common ions. It just says distilled water. Now it says calculate the value of KSP. It already gave us the KSP expression actually right here. But it's just like any other equilibrium constant. It's products over reactants, excluding solids, gases, and liquids. So just the aqueous components. So our KSP is 0.043, which was the value for Sr2 plus given to us, 0.043 times 0.086, and that is squared, and that gives us 3.2 times 10 to the negative 4th. Okay, and final problem, part C. The student prepares the second saturation solution of this in this. So we've got a common ion of Sr. So instead of water, they used a common ion Sr2 plus. Will the value of OH minus in the second solution be greater than, less than, or equal to the value in the first solution? Justify your answer. So let's write out our KSP expression. KSP was Sr2 plus times OH minus squared. Now KSP is constant because we have constant temperature. So let's assume we increase Sr2 plus. So we increased Sr2 plus because we added Sr2 plus instead of using water. So if we increase Sr2 plus, that means OH minus must decrease for this KSP to remain constant. So we would say it is less than. Cool. You guys are going to do great on the AP exam. I love you all. I'm proud of all of you. And you're going to kill it, kill it, kill it, kill it, kill it.